The comet had not yet revealed its name to the world when the first strange images began drifting through the quiet channels of astronomical networks. Before the papers, before the debates, before the skepticism hardened into a familiar rhythm, there was only a smear soft diffuse undeniably present yet defiantly unreadable. Against the star-stung canvas of interplanetary darkness, the Rubin Eye Atlas moved like a ghost, whose outline refused to stabilize as if the universe itself were shielding its contours with a steady, deliberate hand. The cameras aboard the Mars Reconnaissance Orbiter machines, built with an almost monastic precision, turned their gaze outward and prepared to do what they were engineered to do: reveal. Instead, they returned ambiguity. Not absence, not failure, just a glowing disorder of light drifting outward like wisps of powdered glass suspended in the void. The smudge was unsettling not because it lacked detail, but because that absence felt intentional. A haze where there should have been structure. Luminosity where there should have been shadow. Every pixel suggested that clarity existed somewhere behind the fog just beyond the reach of the world's most advanced eyes. The data stream looked wrong in a way that scientists recognized instantly. Not noise, not instrumental failure, but something misaligned between expectation and reality. As if the comet were present yet unreachable, close yet veiled. Far below on the turning blue world humanity calls home, someone sat in a backyard with a telescope worth less than a smartphone. And their view impossibly and conveniently showed more. Shapes, filaments, a faint ring bending around the nucleus like a breath frozen in motion. Jets thin and angular etched against the blackness in a geometry that looked almost deliberate. Not sharp in an artistic sense, but sharp relative to what billion-dollar optics had delivered. These amateurs stitched across continents and time zones connected by nothing more than curiosity and sleeplessness, found themselves bearing witness to a paradox they could scarcely articulate. Their tools were humble, their methods were imperfect, and yet the cosmos had offered them clarity. The contrast was immediate and jarring. Spacecraft instruments designed to detect the faintest whisper of light across interplanetary distances saw nothing but haze. Backyard telescopes buffeted by atmosphere and city light saw crisp evolving forms. There was no precedent for this. No comforting textbook chapter, no familiar quirk of optics or calibration drift that could sanitize the contradiction. The paradox arrived fully formed like an equation missing its center term, daring observers to explain how simplicity had outperformed sophistication. In the slow, contemplative cadence of scientific tradition, clarity usually emerges through accumulation. More data, more measurements, more processing, more refinement. But here was a situation where more sharpened nothing. More only thickened the smudge. More left the nucleus locked beneath the layers of glare and diffusion. The blur was stubborn, uncooperative, as if shaped by forces not yet named. The comet glowed yet refused to be seen. There is a loneliness in such moments when the universe withholds its structure when human instruments reach but cannot touch. Every generation of astronomers inherits the same silent compact that the cosmos will reveal itself to persistence. But 3 Atlas whispered an older truth, one that predates telescopes and mathematics. Sometimes the sky shows what it chooses, not what we demand. The paradox took shape quietly at first. A few mismatched images, a handful of observers asking whether anyone else had noticed. Then a wave comparisons overlays processed frames, raw frames, forum debates stretching into dawn. And beneath all the chatter, the unmistakable tremor of something unspoken, a sense that the object was not hiding because of distance or speed or poor lighting, but because visibility itself had become the mystery. The cosmos has hidden things before, entire galaxies cloaked in dark matter, stars wrapped in dust, worlds concealed by their own cold atmospheres, but those mysteries obeyed rules. They dimmed the universe, predictably, impulsively, consistently. 3i Atlas dimmed selectively. It blurred when watched by the machines best equipped to reveal it. It sharpened when seen by hands untrained by lenses untouched by institutional calibration. As the object drifted closer to the inner solar system, its paradox grew more pronounced. Spacecraft reported a featureless glow uniform and unhelpful. Ground-based amateurs reported structure shifting gently over nights, a rotation of brightness, a curling arc, a tail that forked in ways not yet modelled. Some observers hesitated to post what they had captured, worried that their images would be dismissed as artifacts or processing illusions. Others posted boldly inviting scrutiny, asking whether the universe had ever behaved like this before. It had not. Between these two streams of vision, one engineered for precision, the other assembled from curiosity, hung a question too large for any one observer to articulate. Why in a universe ruled by the symmetry of physical law would expensive instruments be blind while modest ones glimpsed coherence? Why would clarity emerge from imperfection and dissolve under perfection? The contradiction felt philosophical as much as scientific, like a lesson folded into the darkness, urging humanity to reconsider the relationship between observation and truth. In time, the paradox would acquire a name, the visibility paradox, a phrase that sounded abstract, almost academic, until one considered what it implied that the object itself might be sculpting the way it was seen. That light reflecting from its surface carried not just illumination, but a story warped by the environment around it. That observation was not a neutral act, that the universe was speaking through distortion. The comet continued its approach in silence, trailing vapour and mystery in equal proportion. No radio bursts, no irregular pulses, no obvious signatures of anything other than ice dust and motion. And yet the contradictions remained shimmering like heat above a desert horizon, daring humanity to look closer and suffer the discomfort of uncertainty. In the quiet hours before dawn, when amateur telescopes hum softly in suburban yards, and spacecraft circle Mars with their unblinking sensors, a single truth clings to the shifting blur somewhere beneath the glow, beneath the haze. Beneath the paradox itself lies a nucleus that has crossed from another star to reach this moment. And that nucleus, hidden, shielded, or simply misunderstood, holds answers that wait beyond the reach of our current eyes. For now the universe allows only glimpses. The first true glimpse came not from Earth, but from a red world whose thin atmosphere drifts like a fading memory. Mars, silent and cold, had become an unlikely astronomical outpost. Its orbiting sentinels machines, built with patient precision, circled above its ochre plains, gathering data, not for the planet beneath them, but for the interstellar visitor, sweeping past on its inward glide. The Mars Reconnaissance Orbiter, veteran explorer of Martian canyons and dust-churned valleys, prepared to turn its eye outward for a target no mapping algorithm had ever been designed to follow. Its cameras were built to study rock layer sediment fans, ancient riverbeds scarred by time. But engineers had long known that space exploration often demands improvisation, and so the high-resolution imaging science experiment, Highrise, pivoted toward the black. Against the void, far beyond the orbit of Mars itself, a single moving point of light carried the momentum of another system's history. 3I Atlas, the third interstellar object ever recorded by human technology, crossed the field of view. Anticipation pooled in mission centers scattered across Earth. Observers waited for detail, any detail to emerge. They spoke in low voices, monitored telemetry, refreshed data streams like ritual. The spacecraft had executed its commands perfectly. It had aimed its optics at coordinates refined through days of orbital predictions, the exposure completed. The photons, having bounced off an object from another sun, threaded their way across 30 million kilometers of emptiness before touching the sensor. A journey long enough to feel mythic, precise enough to feel intimate. And then the image loaded. Not sharply, not dramatically. Just a slow unfurling of pixels across a screen, the universe revealing itself in increments. The shape took form, or rather the absence of shape. A diffuse patch. A glow blurred into formlessness. A smear that seemed to expand outward. Luminous, yet indecisive. The data scientists leaned forward. The comet, the interstellar traveller they had tracked so carefully, looked less like an object, and more like a memory of one. The room quieted. Someone adjusted contrast. Someone zoomed in. Someone checked timing stamps and calibration files, confirming that nothing had malfunctioned. The raw images remained the same, a hazy silhouette lacking any nucleus jets or discernible structure. A featureless bloom. Highrise had seen Mars in breathtaking clarity, boulders, dunes, cliff faces measured in inches. But staring into interplanetary dark, it now struggled against something it could not pass. Its exposure optimized for rocky terrain, and sharp boundaries flattened into a gentle fog around the comet. The machinery had obeyed physics as written. The universe had answered with physics as experienced. Across mission sites, interpretations diverged. Some saw the smudge as predictable, even expected an interstellar object wrapped in a thick coma blurred by distance motion. and the limitations of imaging from orbit. Others felt an undercurrent of disquiet, a sense that the instrument's blindness exceeded what the known variables allowed. Beneath the diplomatic language of preliminary statements, a quiet unease began to take root. It was the kind of unease that grows not from error but from unfamiliar truth. At the same moment, MAVEN, the Mars Atmosphere and Volatile Evolution mission, captured the object in ultraviolet. Unlike Highrise, MAVEN was built to trace gases plasma and the thin exosphere of Mars itself. When it turned toward 3I Atlas, it detected an extended hydrogen envelope cold and ghostly. The signal suggested that water was indeed sublimating from the comet's surface and breaking apart under solar radiation. In theory, this should have been reassuring a sign of ordinary cometary activity. But the hydrogen cloud was larger, stranger, and more diffuse than models predicted. It bloomed like a pale shroud around the nucleus, a nucleus no one could yet see. Down on Mars's surface, Perseverance lifted its gaze from Jezero crater. Its cameras built for landscape and geology tracked the interstellar visitor as a streak against the starfield, nothing more than a luminous scratch of movement, but still a contribution proof that this object was present from multiple vantage points affecting instruments differently at every scale. Yet all these views surface-orbit ultraviolet converged into a single riddle. None could describe the object's body, none could delineate the structure beneath its coma, none could answer the question forming like a slow tide in the scientific mind: what exactly was hiding inside the haze? The discovery phase should have been clarifying the moment when instruments align and mosaic a consistent truth. Instead, each dataset layered uncertainty on uncertainty. MRO saw blur. MAVEN saw gas. Perseverance saw motion. But none saw the nucleus. None saw jets. None saw the geometry reported by small telescopes scattered across Earth. The more the spacecraft looked, the less they seemed to see. A paradox had begun to crystallize. It would have been easy to dismiss the earliest contradictions as simple observational mismatch Earth-based telescopes observing through long exposures versus a spacecraft snatching fractions of seconds in flight. But the difference felt too stark, too deliberate. Something about 3I Atlas was interacting with these sensors, shaping what they recorded, bending visibility, as if visibility itself were a variable. The scientists did what scientists always do: they composed hypotheses. They debated coma density. They discussed phase angles and dust scattering. They checked models of forward scattering, radiative transfer coma symmetry. They asked whether the object's composition could be more exotic than assumed, whether the dust grain size distribution might explain the disconnect. They asked whether geometry or timing, the subtle choreography of observation, might be enough to blur detail. And yet still beneath all explanations, the essential contradiction remained untouched. Why could some see structure while others saw only glow? 3I Atlas had drifted into the inner solar system carrying nothing but its frozen chemistry and the inertia of a distant star's birth. But with the first images from Mars, it had delivered something more: a scientific wound shaped like a question, a fracture between expectation and evidence. The kind of fracture that makes careers upends theories and forces humanity to step deeper into the shadowed corridors of the unknown. It would not be the last. The paradox deepened not in laboratories, not in mission control centers, but in the quiet domestic corners of Earth, driveways, rooftops, backyards where astronomers worked under the slow pulse of porch lights and cooling summer air. As the official images from Mars drifted across the scientific world with their blurred, indistinct glow, amateur observers began posting their own results. And what they posted did not agree. Their frames showed a comet that behaved like a chameleon between instruments sharp-edged, structured, alive with form. The contradiction was not subtle. Their telescopes, small by professional standards, burdened by atmospheric turbulence, aligned by hand rather than hydraulics, should have produced soft, imperfect images. Instead, they revealed detail that should have belonged only to spacecraft. Threads of brightness that resembled jets, a faint curving loop suggestive of a shell or ring. Regions of asymmetry shifting over hours as though some mechanism in the coma pulsed with the comet's rotation. The images were not uniform, they varied in clarity, strength, colour. But they carried a coherence that amateur astronomy rarely achieves by accident. A pattern emerged. In a suburb in Arizona, an observer recorded 3 narrow plumes angled like the arms of a broken compass. In rural France, someone captured a luminous arc curling around the nucleus, like the early sketch of a halo. In South Africa, a long exposure stack revealed a bifurcated tail, two diverging streams rather than one with delicate internal structure. The images grew in number, they grew in confidence. People annotated them, overlapped them, calibrated them, and the features they described, though subtle, echoed one another across continents. The first reaction was skepticism, not from malice but from habit. Amateur images can deceive. Software can introduce artifacts. Overprocessing can invent shapes where none exist. Yet the consistency among these independent observers made coincidence an uncomfortable explanation. These were different telescopes, different sensors, different skies, and yet the same structures whispered through their frames like an echo travelling the curvature of the Earth. Forums buzzed in the dark hours, users cross-referenced timestamps. They compared filters, hydrogen alpha broadband luminance red continuum. They examined raw frames to rule out oversharpening. One thread circulated a side-by-side comparison NASA's $1 million blur beside a backyard 12-inch reflector's structured glow. The juxtaposition felt almost subversive. It raised a question no one wanted to ask aloud. Why could an amateur reflecting tube costing a few $100s see what a spacecraft orbiting Mars could not? Some suggested timing. Perhaps the comet was more active when amateurs observed its jets flaring and subsiding in ways spacecraft had missed. Others suggested that long exposures minutes stacked atop minutes could integrate faint features that Highrise's short exposures smeared into fog. But this explanation felt thin. Highrise was designed for clarity, for precision and order of magnitude above anything Earth-based. That it could not detect structure at all, while amateur images repeatedly hinted at its existence, unsettled even the most cautious thinkers. The more the images spread, the more the paradox sharpened into a cultural moment. Is NASA missing something? Whispered one post. Why are amateurs seeing rings? Asked another. Someone jokingly suggested that the comet possessed a sense of humour, showing its true face only to hobbyists. Others suggested more speculative causes, plasma scattering, phase angle illusions, unfamiliar chemistry. A few voices fringe, but Ernest murmured that the object might be choosing how it appeared, as though visibility were not simply a function of optics, but of the comet's internal state. Most rejected that idea, but the unease lingered. As more amateurs uploaded their night's work patterns in brightness, hinted at rotational modulation, subtle shifts suggesting a nucleus turning beneath a translucent veil. The jets, if jets. They were rotated positions in a rhythm that made sense only if the underlying structure was real. The ring-like arc appeared in images separated by oceans and time zones, consistent in curvature, inconsistent in brightness. It seemed to shear and fade as though made not of matter but of effect. Perhaps a boundary in the coma where particles aligned or scattered light in unusual ways. Some observers hesitated to share. They worried the community would dismiss their work as wishful thinking. But something about 3i Atlas loosened the usual hierarchy between professionals and amateurs, perhaps because the object itself defied those boundaries, offering clarity to the simplest tools and resistance to the most advanced. The paradox democratized the mystery. Anyone, anywhere, with enough patience and cold fingertips, might glimpse a structure no spacecraft had yet revealed. A few amateurs took their analysis deeper. They created motion maps. They tracked the subtle drift of brightness peaks over nights, attempting to infer the nucleus's spin state. They compared their images to simulated comet at various phase angles. They found nothing that matched easily. The comet behaved like a natural object in its broad strokes, its tail pointing away from the sun, its brightness rising as it approached perihelion, but the fine structure resisted classification. There was something inconsistent about its behaviour, something almost layered, as though one set of features belonged to a diffuse dust-laden outer coma, and another belonged deeper within, hidden from spacecraft, but occasionally glimpsed from Earth under the right alignment of wavelength exposure time and atmospheric transparency. Scientists were slow to comment. The professional community often moves cautiously when amateur data seems to contradict spacecraft imagery. But quiet murmurs began in private channels, in Slack threads, among astronomers, in late-night emails between colleagues. Some wondered whether the high-end imaging pipelines used for spacecraft could be suppressing faint structure, accidentally erasing subtle shapes as noise. Others asked whether the comet's environment might be interacting differently with short-exposure instruments. A few asked whether the comet's plasma conditions, whatever they might be, could be producing refractive distortions. A hypothesis had begun to form in shadow colourless and unspoken, that there might be layers to 3i Atlas's presence, layers that revealed or concealed depending on the type of observation, layers that behaved like a veil not because they wished to hide but because their physical nature bent light in ways humanity barely understood. The amateurs unknowingly had stumbled into the heart of the paradox. They had seen too much because they looked too simply. Their telescopes' limited but patient captured what precision sometimes filtered out the faint structures that lay on the threshold between the visible and the distorted. What they saw was not definitive, but it was enough to bruise certainty, and once certainty is bruised, mystery can enter. The paradox now had two halves, a blur that resisted clarity, and a clarity that resisted explanation. Between them lay the truth not yet visible, not yet named, moving through the solar system with the slow grace of an object older than our species. Backyards had become observatories, hobbyists had become unwitting pioneers, and 3i Atlas, wrapped in its silent haze, continued forward its secrets intact, its outline still wavering between revelation and refusal. The earliest days of any interstellar object's arrival produce a rhythm of discovery that feels almost ceremonial. Telescopes pivot, software hums, observers trade coordinates with the urgency of storytellers passing down a myth before dawn. But when 3i Atlas entered this choreography, the rhythm faltered. The object arrived like a half-remembered song, familiar in its trajectory, yet unfamiliar in every observable detail. To understand how the paradox began, one must trace the fragile threads of its first detection, the nights when numbers flickered into meaning and the world did not yet know it was being visited. It began with motion, a faint, fast-moving point that drifted against the stellar background just subtly enough to catch the attention of survey algorithms tuned to detect wanderers. The Atlas survey scanning the skies for asteroids that might one day trouble Earth logged a single streak whose velocity was too high for a solar-bound body. Its eccentricity greater than 1 marked it immediately as interstellar, a visitor, not a resident. When the Minor Planet Center published the coordinates, astronomers across Earth turned their telescopes skyward. They did so with the same mixture of excitement and restraint that had accompanied the detection of Oumuamua and 2i Borisov, knowing that interstellar objects arrive, rarely leave quickly, and reveal themselves only in fragments. Early photometry from small observatories painted the first picture. The object brightened steadily, though not in a way entirely consistent with a typical comet. The brightening curve rose too quickly at certain intervals, too slowly at others, as if driven by a volatile inventory that did not map cleanly onto the templates built from solar system comets. The tail grew faintly visible long before water ice should have sublimated at that distance. Meanwhile, colour indices, measurements of brightness across multiple filters, hinted at a redder-than-usual body reminiscent of Kuiper Belt objects. Nothing here was definitive, but each element nudged the object toward the category of unusual. And in the early days of discovery, unusual is the currency of curiosity. Professionals took notice. Observatories in Hawaii, Chile, China, and Europe collected early spectral low-resolution glimpses of the coma's molecular composition. These initial readings were murky, distorted by distance and low photon counts. Yet even through the noise patterns emerged an unexpectedly strong carbon dioxide signature, faint water, and a continuum slope that strained familiar classification. Those who studied volatile evolution murmured quietly among themselves. A comet venting carbon dioxide at such large distances implied either exotic chemistry or a nucleus unusually exposed to radiation. But the object was still too far, too dim, too steeped in the interstellar chill for definitive statements. As more data accumulated, researchers plotted its orbit backward. Where had it come from? Could its path be traced to a known star system, or at least to a stellar neighbourhood? The solutions diverged. One arc suggested a distant origin near a cluster of young stars. Another pointed toward the empty spaces between constellations where no recent stellar encounters could explain its ejection. The inbound trajectory carried no obvious signature of gravitational scattering. Nothing about its momentum suggested a recent encounter with a dense environment. It seemed older, quieter, the kind of object that had drifted through interstellar space for millions or billions of years, shaped by cosmic rays and cold until chance brought it into humanity's view. Still, these were only clues, patterns, shadows. The full strangeness of the object had not yet emerged. not until the Discovery teams compared its early brightness measurements to its predicted nucleus size. If it were as small as initial estimates suggested, a kilometre or two across its brightness was too high. If it were larger 5 or 6 kilometres, its acceleration under solar heating was too strong. These mismatches seemed trivial at first. Many comets show nonlinear behaviour early on. But later, as the paradox sharpened, these incongruities would be remembered as the first hints that 3I Atlas did not conform to simple categories. The other telling clue was buried in the first polarization measurements. Even with limited data, one could see the beginnings of a negative branch deeper than expected. Light scattering off the dust carried an imprint of surface composition, one that whispered of complex organics, large grains, and perhaps an irradiated crust. The polarization curve sketched the outline of a surface shaped by a history humanity could not yet read. These early signals, the unusual brightening, the spectral imbalance, the strange scattering behaviour were not definitive enough to cause alarm. But they created an atmosphere of gentle unease. Scientists spoke in cautious language situating the object within the normal distribution of interstellar possibilities. They were careful not to overstate its difference, careful not to repeat the speculative fervour that had surrounded Oumuamua. But privately they tracked each new data point with the sense that this object was drifting toward a place beyond familiar models. Meanwhile, in amateur communities, the discovery played out differently. They saw a small, fast-moving visitor from another star, not the chemistry, not the orbital mechanics, but the romance of the idea. They watched its magnitude rise night by night. They compared notes on visibility in modest telescopes, and unknowingly some among them began recording the very features that Highrise would later fail to detect. Their earlier stacks, grainy, imperfect, but heartfelt, showed faint jets before any spacecraft image had even been captured. The disconnect had not yet formed into a paradox. It existed as two parallel stories told by two types of observers, one careful, methodical, grounded in known physics, the other passionate, curious, attuned to the smallest shift in light. Only later would these stories intersect and contradict each other. Only later would the scientific world be forced to ask whether the interstellar visitor had been revealing different faces to different observers. In those first days, though, 3I Atlas was simply a new point on humanity's sky, a wanderer entering the stage of observation, waiting patiently beneath the starlight to test the limits of our instruments and the assumptions behind them. The data was sparse, the mystery was young, and the veil had not yet begun to fall. Not yet. There are moments in astronomy when an object does more than surprise, it resists the very frameworks built to understand it. 3I, Atlas, entered that realm gradually quiet, at first polite in its disobedience. But as the measurements deepened, as photometry sharpened and orbital models converged, something became difficult to ignore. The interstellar visitor was violating expectations at nearly every scale. It was not shattering laws of physics, nothing so dramatic, but it was bending them, pressing against the edges of familiar behaviour in a way that felt deliberate, as though the object had been shaped in an environment where the rules were the same, yet the outcomes were subtly different. The simplest rule it resisted was brightness. Comets brighten as they approach the sun, that much is textbook. But 3I Atlas brightened unevenly in fits, and starts with sudden increases not easily tied to rotation or outbursts. At distances where water ice should be dormant, it glowed too intensely, implying activity driven by something other than water. Carbon dioxide or carbon monoxide, perhaps. But even those volatiles known for sublimating at greater distances could not fully account for the early surge. Something about the distribution of material on the nucleus, its temperature gradient or layered structure, felt alien, as though the internal inventory had been sculpted not by the sun's gentle heating cycles, but by a different star, a different dawn. The second rule it resisted was shape, specifically how the coma developed. A typical comet forms a predictable envelope of dust and gas surrounding its nucleus. The envelope density falls off smoothly. The symmetry is rarely perfect, but usually intelligible. 3I Atlas, however, produced a coma that refused coherence. Ground-based measurements indicated asymmetry, localized bright zones shifting over time, whereas spacecraft saw near-perfect uniformity. The contradiction became more pronounced as more eyes turned toward the object. Some observers hinted at arcs or thin structures that traced gentle curves around the nucleus. Others saw none at all. It was as if the object drew its veil differently depending on who looked at it. Its motion introduced the third disobedience. Deviations from gravitational trajectories are not inherently strange. Outgassing creates tiny thrusts that nudge comets slightly off course, but the acceleration observed in 3I Atlas was disproportionate to its visible activity, too large for the amount of material apparently leaving its surface, too persistent across multiple epochs, and it grew in ways that standard sublimation models struggled to match. When scientists attempted to reconcile the acceleration with dust production rates, the values landed in uncomfortable territory. Either the comet was shedding more mass than observed, or the forces involved included mechanisms not fully accounted for. The non-gravitational acceleration was not chaotic, it followed a pattern, and patterns demand explanation. Then came the polarization anomaly. Light reflected from the comet carried a signature that was not simply unusual but unprecedented. A deep negative polarization branched sharper and earlier than any recorded for a comet or asteroid. It suggested particles either too large, too structured, or too charged to match standard dust models. The inversion angle, where polarization flipped from negative to positive, occurred at an angle that mapped to no known analogue. The comet behaved like an object with dust properties belonging to neither solar comets nor icy bodies from the Kuiper belt. It hinted at formation in a chemically exotic environment, perhaps a colder region, perhaps one exposed to harsher radiation for longer times, perhaps both. Each anomaly was survivable alone, each had an escape route through parameter space one could adjust. Particle size distributions tweak, sublimation models invoke heterogeneity on the nucleus's surface. But anomalies accumulate, they stack, and eventually the stack grows tall enough to cast a shadow. That shadow deepened with the spectral data. Instruments across the world, from modest spectrographs to the James Webb Space Telescope, measured volatile ratios that seemed almost combative in their divergence from norms. Carbon dioxide dominated the outgassing profile, dwarfing water by a factor unseen even in the coldest solar system comets. The CO2-H2O ratio placed the comet not at the edge of known chemistry, but beyond it, a full deviation into territory where standard formation scenarios strained and cracked. This wasn't simply a cold comet. It was chemically lopsided, too much of one volatile, too little of another. The imprint of an origin far from any sun-like warmth. Astronomers attempted to fit the object into familiar classifications. It resisted. Tried to align its dust properties with known families. It resisted. Placed it alongside 2I Borisov, the first confirmed interstellar comet. It resisted. Compared it to Oumuamua, itself an outlier, it still resisted. Still. Yet the rules it bent revealed something deeper. The Atlas did not violate physics, but rather exposed gaps in the assumptions used to apply physics to interstellar objects. Its behavior suggested there were regimes of cometary evolution not yet understood. Combinations of chemistry, temperature, and radiation exposure that no solar system body preserved. Conditions that could sculpt a nucleus with properties so uncommon that even our most generous models seemed provincial beside it. But the greatest contradiction of all, the one that stitched every smaller oddity into a single line, was the visibility paradox. Why did the comet sharpen under simple optics and dissolve under advanced sensors? Why did digital pipelines suppress the very features that long exposures revealed? Why did the core seem invisible at short wavelengths yet structured at others? A cosmic rule whispered in the background: objects in plasma behave differently than objects in vacuum. Charged environments distort light, shift polarization, absorb frequencies, refract directionally. And if 3I Atlas carried such an environment, dense, active, unstable, it could become selectively visible, a creature of wavelength and geometry. It bent the rule of visibility itself. By the time astronomers acknowledged that the comet could not be neatly accommodated within current models, the object had already entered the realm of mystery. Not a mystery of supernatural origin, but of physics, operating at the edges of human experience where the interplay of dust, gas, charge, and light behaves in ways uncharted. The rules had not failed, but they were insufficient. And in that insufficiency, the comet revealed something essential: the universe still contains behaviors that elude the tools built to interpret them. 3I Atlas was not breaking the laws of physics. It was reminding humanity that understanding those laws fully is still a work in progress. The deeper scientists looked, the less the object resembled the quiet, predictable physics they had expected. Anomalies, once scattered like isolated footprints, began arranging themselves into patterns subtle, at first, then unmistakable in their coherence. Every measurement, every refinement of orbit, every new spectrum added a brushstroke to a portrait that refused to stabilize. The deeper investigation into 3i Atlas did not clarify the mystery, it sharpened it. The first sign of trouble emerged from the orbital residuals. As more observations poured in from ground-based telescopes from Mars, orbiters from long baseline tracking stations, the calculated trajectory drifted from its gravitational prediction. At first, the deviation was small enough to ignore, lost in the numerical static that accompanies any early-stage orbit determination. But as the error bars shrank, the discrepancy remained. The comet was not where Newtonian gravity alone said it should be. It accelerated slightly outward from the Sun, as though pushed by a faint persistent hand. This was not unprecedented. Cometary outgassing can produce thrust. But when scientists quantified the required mass loss rate to generate the detected acceleration, the numbers strained credulity. Visible outgassing did not match the momentum needed. If the comet was shedding mass vigorously, where was the evidence spacecraft saw no powerful jets? Spectra showed activity, but not enough to justify the force measured. The mismatch grew sharper with every data point. Researchers revisited the dust production models. These models rely on estimating how much dust and gas a comet releases as it warms. But the coma surrounding 3i Atlas, the expanding cloud of dust and vapor, seemed too smooth, too featureless, too empty of strong density gradients. A comet losing mass fast enough to account for its trajectory should display violent jets or fragmentation events. Instead, the coma resembled a diffused shroud, more like a veil than an engine. This contradiction did not fade with further inquiry. It deepened. Next came the dust size distribution. Polarimetry suggested unusually large grains, far larger than those typical in solar system comets. Large grains require substantial force to lift from a surface. They resist solar pressure and drift slowly. Yet the coma contained an abundance of these heavy particles. Something had carried them upward. Something with the strength of a directed jet, yet no such jets were visible to spacecraft. The amateurs saw faint radial structures, yes, but nothing that matched the magnitude required to loft millimeter-scale grains. The dust was also strangely homogeneous. Cometary dust is usually a chaotic mix of particle sizes, shapes and porosities. But models attempting to reproduce 3i Atlas's polarization curve converged towards shockingly uniform parameters, as though the dust had been processed or sorted somewhere in the object's long interstellar journey, as though something cosmic raised thermal cycles, or something more unusual had sifted the dust into a narrow band of properties. Spectroscopy added its own layer of strangeness. The carbon dioxide spike so large it defied standard formation scenarios demanded explanation. Cosmic ray processing could generate this imbalance over millions of years by converting carbon monoxide to carbon dioxide. But that did not explain the weakness of water signatures. Water decomposition produces hydroxyl radicals detectable in radio wavelengths. These were present, yes, but underwhelming compared to the CO2 signal. The nucleus seemed to hold layers of volatile ice in proportions unrecorded anywhere in the solar system, and the closer it drew to the Sun, the more this imbalance intensified. Traditional comets reveal richer chemistry as heat unlocks deeper layers. 3i Atlas revealed almost nothing new, only more carbon dioxide, a monotony so extreme it felt unnatural. When James Webb's mid-infrared observations were released, they sharpened the profile further. The thermal emission curve did not match any standard thermal model. The nucleus appeared warmer than expected in some wavelengths, and cooler in others, a sign of surface heterogeneity, or perhaps an insulating layer of dust. Yet the thermal gradient across the coma did not match predictions either. Portions of the coma remained surprisingly cold even when illuminated by sunlight. The temperature distribution traced an outline inconsistent with a simple spherical outflow of gas. It was as if parts of the coma were shielded from heating. Magnetometers aboard MAVEN provided the next surprise. As the spacecraft observed the comet from Mars orbit, it registered fluctuations in the local magnetic field. These fluctuations were small but persistent, far above background variation. The patterns hinted at interactions between the solar wind and a localized plasma environment around the comet. But MAVEN was too far to detect structure. It only sensed the signature of turbulence. Something around 3i Atlas was stirring the solar wind. Meanwhile, Earth-based radio telescopes detected hydroxyl emissions as expected from water decomposition, But inconsistencies emerged in the line ratios. These ratios are normally stable, dictated by quantum mechanics and the pumping conditions of the coma. But in 3i Atlas they wavered unpredictably. Subtle shifts, yes, but shifts that suggested collisional excitation, elevated electron densities or magnetic influences near the emission region. In other words, plasma. By this point, the deeper investigation had amassed a constellation of anomalies. None alone broke the laws of physics. None alone demanded reinvention of comet science. But take them together, non-gravitational acceleration with insufficient mass loss, an obscured nucleus, homogeneous large-grain dust, CO2-dominated chemistry, thermal inconsistencies, magnetic field fluctuations, radioline anomalies, and a pattern emerged that no one could ignore. The comet behaved as though wrapped in an environment not typical of natural comets. An environment dense enough to redistribute heat, scatter light, accelerate dust and distort radio signals. Something capable of obscuring jets, diffusing visible light, and altering the effective visual geometry depending on wavelength and exposure time. A plasma structure, a sheath of ionized gas sustained by outgassing and solar wind interaction. Perhaps. But if such a sheath existed, it needed to be far denser, far more stable and far more structured than anything seen around typical comets. Somewhere among the data, the first whisper of a hypothesis glimmered like a distant star emerging from twilight. Perhaps the object was surrounded by a plasma veil. A veil that thinned at times, thickened at others, interacting with light selectively, and creating the strange duality of images spacecraft blind amateurs seeing structure. And if that veil existed, if plasma was the architect of the blur, then the mystery was no longer one of missing data. It was one of misunderstood physics. A comet behaving in ways that challenged assumptions about how interstellar objects carry their long histories. A nucleus communicating through distortion. A visitor cloaked not by intent but by the complexity of its own environment. Deeper investigation did not solve the paradox. It inverted it, turning the blur into a clue. The deeper one peered into the haze around 3i Atlas, the more it resembled a boundary, a threshold between what human senses could detect and what still remained hidden beneath. The comet was not simply faint, it was concealed by a phenomenon of its own making. By the time the data had woven itself into a coherent unease, scientists found themselves standing before the edge of an idea none had planned to entertain. It began as a whisper, an informal comment in a late-night email thread, a stray remark in a conference hallway, a quiet acknowledgement between colleagues reviewing inconsistent imaging results. Something about 3i Atlas behaved as though the space around it were not empty but alive, as though the medium between comet and observer, normally transparent, normally passive, had become an active agent shaping what could and could not be seen. This whisper soon acquired a name: the plasma veil hypothesis. The idea was not born from speculation but from necessity. There was no single anomaly that forced it into existence. Rather, it emerged from the accumulated weight of mismatches, the conflicting images, the thermal irregularities, the magnetic turbulence detected from Mars orbit, the unexpected uniformity of large dust grains, and the CO2-dominated chemistry that hinted at deep radiation processing. Each clue alone was ambiguous. Together they pointed toward an environment that did not behave like the diffuse gentle comi familiar from solar system comets. To understand this hypothesis, one must step backward into the nature of plasma itself. In astrophysics, plasma is not exotic. It is ordinary, perhaps the most common state of matter in the universe. The sun is plasma. The solar wind is plasma. The auroras dancing above Earth's poles shimmer in the currents of plasma caught within magnetic field lines. Plasma is dynamic, reactive, sculpted by electromagnetic forces that ripple through the cosmos. But plasma does not remain uniform. It clumps, swirls, forms filaments, wraps itself in sheets and arcs. It carries electric currents and can sustain magnetic fields, sometimes stable, sometimes chaotic. And under the right conditions involving ionization from ultraviolet light, magnetic compression, from solar wind pressure or outgassing of certain volatile species, plasma can form dense structures around a body, structures that refract and scatter light. This was the heart of the hypothesis that 3i Atlas had produced or inherited a region of dense ionized gas surrounding it, a veil, a sheath, a cocoon capable of disrupting visibility at high resolution, while leaving longer exposure, lower frequency observations less affected. The physics did not require fantasy. A comet with unusually high CO2 output generates abundant gas capable of ionization. Interstellar radiation accumulated over millions of years could crack its surface layers into conductive materials. Solar wind interaction near the inner system could compress ionized gases into a shell, rather than dispersing them into a tail. If the object possessed even a weak magnetic field, perhaps remanent magnetization from its formation environment, it could shape the plasma into semi-stable configurations. None of this required the comet to be artificial, only unusual. Yet the implications were profound. Plasma interacts with light in ways that defy simple intuition. High-frequency light scatters strongly when passing through dense electron clouds. Short exposures are dominated by instantaneous turbulence. Instruments optimized for clarity like Highrise cannot integrate over time to average out the flickering distortions. The result: blur-smear loss of structure, a luminous fog. Longer exposures tell a different story. They integrate through variability, capturing faint persistent features that remain stable across minutes rather than milliseconds. Amateur telescopes, with their leisurely imaging cadence, unwittingly became the perfect instruments to peer through a phenomenon that sabotaged the tools normally built for precision. In this model, visibility becomes a function not of size, not of distance, not of reflective properties, but of plasma density, plasma temperature, magnetic topology, and the wavelength of observation. The veil acts like a living lens, sometimes transparent, sometimes opaque, shifting with solar wind conditions. Jets might be visible through one section while hidden through another. The nucleus might appear as a sharp point on one night dissolve, into glow on the next, and the veil could change rapidly. If 3i Atlas had such a plasma sheath, the observed inconsistencies made sudden sense. The deep negative polarization branch perhaps influenced by charged dust grains. The thermal anomalies perhaps created by insulating layers of plasma affecting radiative transfer. The magnetic fluctuations in Marvin's sensors perhaps signatures of intermittent reconnection events along the sheath's boundary. The uneven brightening perhaps tied not to outgassing rate alone but to plasma density spikes. Even the mass loss paradox, insufficient dust to match the acceleration, might be partially solved. Electromagnetic drag from plasma-solar wind interaction can produce measurable force on a body augmenting or mimicking outgassing effects. As the hypothesis took shape, it changed the tone of discussions among researchers. What had first felt like a failure of instrumentation now began to feel like a window into an unfamiliar physical regime. 3 Atlas was not violating physics. It was occupying a corridor of physics rarely observed. Yet the plasma veil hypothesis carried an unease of its own. It demanded that the comet be far more active, far more ionized, far more magnetically structured than any comet humanity had studied. It implied that interstellar comets might carry conditions the solar system seldom produces. It hinted at the possibility that we have modelled Comet incorrectly, that our familiarity with solar system objects had lulled us into assumptions that interstellar debris could expose sharply. And it led to another quieter question, whispered but unavoidable. If the veil behaved so coherently, if it was dense and structured rather than chaotic and diffuse, could some part of it be shaped not merely by passive physics, but by deeper order? Not intense scientists did not entertain that but structure, regularity, a magneto-hydrodynamic equilibrium sustained by forces unique to an interstellar object's long, cold evolution, a veil not designed but inherited. For now, the hypothesis remained a set of equations on whiteboards, simulations on graduate students' screens, speculative papers circulating in preprint archives. Yet its implications had already altered the direction of inquiry. The blur was no longer a flaw to explain away, it was a phenomenon to be studied. A phase of behaviour, a shield perhaps fragile, perhaps temporary, perhaps about to change as the sun's activity grew. The plasma veil hypothesis would soon collide with a test more powerful than any telescope. The sun was waking and a storm was coming. If the plasma veil was a hypothesis born from necessity, what followed was an attempt to understand what such a veil might do, how it might reshape light, disrupt detection, hide structure, or even mimic structure in ways that could confuse every instrument pointed toward 3i Atlas. The deeper the inquiry went, the more the comet resembled not an object simply wrapped in gas and dust, but an entity navigating through layers of its own electromagnetic complexity. The veil became less metaphor and more mechanism, a physical environment built by chemistry, volatility, solar radiation, and time. Light in its quiet obedience to physical law reveals what it can unless something along its path alters the message. Plasma by its very nature is such an agent of alteration. Ionized gas interacts with light through scattering, absorption and refraction. These are not exotic interactions. They are fundamental responses of electrons in a charged medium. But in the case of 3I Atlas, the density composition and geometry of the plasma environment could shift these interactions into regimes rarely witnessed around solar system comets. Imagine photons leaving the comet's nucleus, carrying with them the shape of jets, the silhouette of cliffs, the threads of dust spirals. As they travel outward, they encounter a fog of electrons and ions. Some photons scatter sideways, some lose coherence, others bend along gradients of electron density changing direction by fractions of degrees enough to blur fine features, and others vanish entirely absorbed and re-emitted in random directions, losing all trace of the structure they once carried. At certain wavelengths, especially in the ultraviolet, these interactions become dramatic. Short wavelength photons oscillate rapidly, and plasma electrons respond with equal rapidity, creating interference effects that degrade sharpness. A sensor optimized for visible high-resolution imaging like Highrise becomes vulnerable to such distortions, especially in single brief exposures. The result is a smear, a glow, a featureless bloom that tells more about the intervening medium than the object itself. But longer wavelengths, red light, near-infrared, deep infrared, behave differently. Their oscillations are slower, they pass through plasma more easily, they scatter less, and when captured over minutes-long exposures, their paths average out, smoothing turbulence. Amateur telescopes, with their forgiving filters and lengthy integrations, become accidental instruments of truth. This duality, the blur of high resolution and the clarity of low resolution, becomes the essence of selective visibility. An object that appears hidden to one observer can reveal threads of itself to another, not because the object changes, but because the environment between observer and target does. Researchers began to map the conditions under which the veil would thicken or thin. Plasma density depends on ionization rate, which depends on solar ultraviolet flux. As the comet approached the Sun, ionization surged. But density also depends on gas production, which fluctuates as different patches of the nucleus rotate into sunlight. These fluctuations create a sheath in constant motion, expanding, compressing, shifting. Solar wind interactions complicate the picture further. The solar wind carries its own magnetic field embedded in the flowing plasma. When it meets the comet's outflowing ionized gas, the two fields interact. Reconnection events can occur, sudden realignments of magnetic fields that release energy and reorganize plasma structures. These events can cause rapid changes in visibility conditions, sometimes creating arcs or filaments in the coma that resemble geometric structures. Jets might appear where none exist, their forms traced not by dust but by magnetic tension. This raises a provocative question. Could some of the structures seen by amateurs, rings, arcs, straight-line jets, be emergent properties of plasma dynamics rather than physical outflows from the nucleus? If a dense plasma shell formed around the comet, magnetic pressure could create surface-like boundaries where dust and gas accumulate temporarily, forming arcs similar to bow waves. Long exposures could capture these boundaries as persistent geometry, while short exposures fail to resolve them, showing only noise. At the edge of this hypothesis lies a subtler, more philosophically challenging concept that the veil itself is not simply obscuring the nucleus, but creating a secondary surface, an apparent body shaped by plasma rather than rock or ice. In such a case, the true nucleus could remain hidden indefinitely, its signature blurred into the luminous haze. What amateurs recorded might not be the nucleus at all, but the veil's own luminous architecture, and yet even this architecture was inconsistent. Overnights, faint arcs shifted, jets rotated or vanished. Features that appeared clearly in one observer's frames dissolved into nothing for another stationed thousands of kilometers away. The veil was not fixed. It was a system of currents and turbulence sensitive to solar wind conditions at a scale no spacecraft could measure directly. But the veil could also be stripped. Solar storms, especially coronal mass ejections, compress plasma environments. The approaching storm, predicted to strike 3I Atlas in days, would act like a hammer on whatever sheath surrounded the object. If the veil were real, scientists predicted one of two outcomes. Either the compression would intensify the plasma, deepening the blur into total opacity, or it would tear open the structure, thinning the veil, and revealing the nucleus briefly before the environment stabilized again. The most intriguing possibility was the boundary case where the veil's density oscillated rapidly under solar pressure. In that scenario, observers might see the comet flicker, revealing, concealing, revealing, like a lantern swaying behind a curtain of smoke. There were precedents, though faint. Some solar system comets have shown sudden changes in visibility during periods of heightened solar activity. Ion tails have been severed, comae have collapsed, plasma clouds have expanded explosively. But none had displayed selective visibility so starkly nor sustained such behaviour over so long an interval. Could an interstellar object naturally evolve into a state where its environment masks itself in this way? Models suggested yes, if the object carried a composition unusually rich in CO2 and carbon-bearing ices, if its surface layers had been hardened by cosmic rays into a crust that restricted water release, and if its outgassing pattern concentrated ion production into localized regions rather than uniform outflow. A veil in this context becomes the shadow cast by chemistry, and yet the idea stirred discomfort. Because a veil that hides could also imply a veil that mimics. Plasma can scatter light anisotropically, meaning observers at different angles see different effects. This could explain the conflicting images spacecraft saw, fog amateurs saw structure. But it also meant that what amateurs saw, the faint ring, the filaments, might not exist as physical jets, but as distortions shaped by the veil. The comet could be both revealing and deceiving, not through intention, but through its environment's complexity. The plasma veil hypothesis did not answer every question. It opened new ones. It transformed the object from a simple interstellar visitor into a dynamic, turbulent construct shaped by physics, rarely studied up close. It made the blur meaningful, not a failure of observation, but a signature of something the solar system had never shown us. And it pointed toward the storm approaching from the sun as the moment when theory would meet reality. The veil could not hide forever. Not from the solar wind, not from the storm. Soon 3I Atlas would be exposed either as a comet masked by plasma or as something far stranger waiting behind the glare. The sun had been restless for weeks when solar physicists issued their warning. A coronal mass ejection, massive, fast, and magnetically complex, had erupted from the solar surface, unfurling outward like a luminous tide. Forecast models traced its trajectory not only toward Earth and Mars, but directly across the path of the interstellar visitor, already wrapped in its enigmatic glow. Space weather centres around the world pulsed with quiet urgency. If the plasma veil surrounding 3I Atlas was real, then the storm would not merely disturb it, it would challenge it, stress it, perhaps even tear it open. The object's greatest secret, whatever shape hid beneath the haze, would soon face a force far stronger than human instruments, the wrath of a star. Solar storms shape the inner solar system with an authority older than planets. The solar wind, normally a steady river of charged particles, becomes a torrent during coronal mass ejections. Electrons and protons accelerate to extraordinary speeds. Magnetic fields twist and snap, dragging themselves across millions of kilometers. The effects ripple outward, bending comet tails, disrupting spacecraft, stirring auroras into cascades of light. For fragile cosmic structures, dust shells, plasma sheaths, ion tails. These storms are moments of reckoning. In the case of 3I Atlas, the storm approached with exquisite timing. Too early and the object would have been too distant, too cold, too quiescent for dramatic change. Too late, and the veil might have dispersed naturally as the comet neared its activity peak. But now the solar storm raced forward as the object entered a region where its plasma environment was densest and its volatile release strongest. The collision would not be gentle. Researchers proposed competing predictions. Some argued the storm would compress the plasma veil. Under heightened solar wind pressure, the ionized gas could be squeezed closer to the nucleus, thickening the veil until the object became fully opaque. Imaging attempts might show nothing but a swollen glow, featureless and impenetrable, a cosmic lantern wrapped in cotton. Others believed the opposite. Solar storms can produce severe erosion of cometary plasma environments. If magnetic reconnection occurred between the storm's magnetic field and the plasma around 3I Atlas, large sections of the veil might detach, streaming away in curtains of ionized gas. The veil could shred thinning enough to reveal what Highrise had failed to see: the nucleus, the jets, the underlying geometry. The most intriguing scenario lay between these extremes. Plasma does not behave linearly. It flickers. It oscillates. A strong solar storm could force the veil into rapid cycles of density and transparency, creating a visibility state seldom witnessed a comet blinking in and out of clarity. Observers, both professional and amateur, scrambled to coordinate global monitoring. This was the kind of moment astronomers dreamed of, a natural experiment orchestrated by the cosmos, testing hypotheses at scales no laboratory could reproduce. From Mars, Orbit, Maven and MRO prepared to observe not only the comet, but the shock front of the storm itself. Instruments tuned to measure magnetic fields, electron densities, and ultraviolet emissions waited to capture the veil's reaction. If the plasma layer was real, Maven should detect sudden spikes in ionization. Highrise, though, limited by exposure constraints, might capture changes in coma morphology, even if only as differences in the blur. On Earth, observatories shifted schedules. Radio telescopes aligned their arrays. Polarimeters prepared to track the behavior of scattered sunlight with exquisite sensitivity. Amateurs set alarms for the early hours when the comet would sit low and fragile on their horizons. Some spoke of treating the event like an eclipse, brief, delicate, irreversible. What the storm revealed or concealed would define the comet's nature for years. As the CME approached, atmospheric models simulated the impact zone. The sheath around 3I Atlas, if present, would be no passive bubble. The storm's arrival would punch into it like a hammer through glass. Plasma density would surge. Turbulence would cascade. If the veil had internal structure loops, boundaries, charged dust fabrics, these would light up in ways visible across multiple wavelengths. Jets, if they existed, might brighten suddenly, as recombination events released photons. Dust particles might scatter more strongly as they were accelerated by the shock. Every scenario ended in brightness. The question was what kind. When the first wave of particles struck, Maven recorded the change immediately. The solar wind density spiked. Magnetic field lines twisted. The environment around the comet shifted violently, though the exact forms of these shifts would not be understood until the data was fully processed. For a moment, instruments reported unstable readings, brief chaotic signatures typical of plasma compression events. Then images began arriving. From Earth, long-exposure photographers captured the comet brightening its coma, expanding like a breath taken sharply. Some saw jets sharpen, as if illuminated from within. Others saw a thin arc detach from the comet's tail, a classic disconnection event caused by magnetic reconnection. A phenomenon recorded in other comets, but rarely so clearly. From Mars, the blur changed, not vanished, changed. Highrise, once nearly blind, now recorded gradients within the glow. Not structure, not clarity, but difference, a sign the veil was responding dynamically. Maven's ultraviolet spectrometer detected increased emissions from ionized carbon species, a signature of intense ionization consistent with the disturbed plasma sheath, and the polarity of the scattered light shifted. Polarimetric observations captured changes in orientation that suggested the dust grains in the coma were realigning under new electromagnetic conditions. It was not a reveal in the cinematic sense. The comet did not suddenly expose a rocky surface. No perfect jets materialized. No nucleus glowed naked against the void. But something had changed. The veil had not vanished, but it had thinned, wrinkled, flexed under the solar storm's pressure. Hidden structure, long blurred, now hinted at its outline. The results were ambiguous but exhilarating. The plasma veil had not been disproven. If anything, it had been provoked into visibility, and as the storm continued its passage, the comet drifted onward, still wrapped in its enigmatic haze, but altered like a shape glimpsed through curtains fluttering in a sudden wind. The sky had not yet delivered answers, but it had delivered motion, and motion in science is often the first whisper of revelation. Long before anyone uttered the phrase visibility paradox, the comet itself had already written its explanation into light. The signature lay not in brightness, nor in shape, nor even in the jets that flickered in and out of amateur telescopes, but in the way photons twisted as they touched dust. Polarization, often overlooked and rarely glamorous, became the quiet storyteller of 3I Atlas, whispering truths about the object's surface, its dust grains, and the strange conditions sculpting its luminous veil. Polarization begins with sunlight. The sun emits light in all orientations, waves vibrating in every direction. But when sunlight strikes particles, ice crystals, dust grains, plasma clouds, its vibration becomes biased. The degree of that polarization, and the angle of its alignment reveal the size, porosity composition, and charge state of the scattering particles. In comets, polarization curves follow predictable shapes. A shallow dip into negative polarization at small phase angles, then an inversion around 20-25 degrees, then steady rise. 3I Atlas refused to follow. Its negative polarization branch was deeper than any on record for a comet, more extreme than trans-Neptunian objects, steeper than solar system comets, sharper than irradiated centaurs. The dip reached nearly 2.7%, a value occupying uncharted territory. Worse or better, depending on one's taste for mystery, the inversion angle occurred far earlier than expected. Not 20 degrees, not even 19, but closer to 17. A value no existing models could reproduce without invoking unusual dust properties. Such a signature implies particles that are either extremely large, highly compacted, coated in complex organics, electrically charged, or some combination of all four. The grain sizes inferred were large enough 1/10 of a millimeter scale that typical sublimation processes would struggle to loft them into the coma. Yet there they were scattering sunlight in strange, asymmetric patterns. The dust was behaving like the debris of a surface that had been hardened by radiation for eons, preserving a crust rich in Tholin's carbon chains, nitrogen-bearing organics, and the fractured remains of CO ice chemistry, long mutated by cosmic rays. But polarization also hinted at something stranger: dust alignment. In most comets, dust grains tumble randomly. In rare situations such as strong magnetic fields or charged plasma environments, grains can align, orienting themselves with field lines. This alignment produces polarization anomalies that deviate from expected curves. Some researchers quietly suggested that the depth of the negative branch in 3I Atlas could arise from such alignment. Dust grains carrying surface charges would rotate into preferred orientations if a surrounding plasma sheath imposed electromagnetic order. This possibility was not mainstream, but it carried weight, especially when combined with MAVEN's magnetic fluctuations and the inconsistent radio line ratios. A structured magnetic environment could impact both dust and gas, affecting how photons scatter in ways that conventional models not built for interstellar chemistry or interstellar histories could not accommodate. Polarization also revealed another layer of truth: the dust was fluffy yet coherent. Large grains, rather than fracturing into powder, remained intact. That suggested either cohesive forces or long-term compaction. In the cold reaches between stars, dust can slowly sinter, partial melting and refreezing at microscopic boundaries, producing aggregates robust enough to survive sublimation-driven ejection. Such aggregates scatter light differently from porous grains formed in the solar system. This alone could account for some of the anomalies, but not the entire picture. What made 3I Atlas unlike any studied comet was how its polarization changed with time. The curve shifted subtly as the object approached the Sun, suggesting that the nature of the dust entering the coma changed. Large grains dominated early. Smaller grains emerged later. The surface seemed layered, its outer skin composed of radiation-hardened organics, its interior holding different material properties. This layered behavior aligned with the unusually high CO2 outgassing. If the surface crust was thick, irradiated, and difficult for water to penetrate, subsurface CO2 could vent through fissures or fractured pockets, lofting grains that did not match the smooth, symmetrical outflows of typical comets. Such venting could create faint jets, but if encased within a plasma veil, those jets might not appear as visible collimated streams. Instead, they could blur or refract, producing the faint structures amateurs captured and the total obscuration that Highrise returned. Polarization also provided insight into the visibility paradox itself. Polarized light interacts differently with plasma than unpolarized light. Under certain conditions, plasma can rotate the polarization angle, a phenomenon known as Faraday rotation. If the veil around 3I Atlas was dense enough to produce Faraday effects, then observers using different filters or exposure times would record conflicting shapes. Amateur telescopes with narrower wavelength ranges and longer integrations could observe averages through the distortion yielding stable patterns. Highrise, with its broader visible band sensitivity and short exposures, might see only the instantaneous turbulence blur. Thus polarization offered not just a description of dust, but a mechanism for the paradox. The deeper scientists pushed their models, the more they realized the comet's dust could not be explained solely by chemistry. Something dynamic, perhaps, electromagnetic, was structuring the environment. a veil that collected sorted guided or concentrated dust in ways no solar system object would. A veil that shaped what each observer saw, and then came the final polarization anomaly. The curves returned toward positive values at larger phase angles grew faster than predicted. This implied particles with reflective surfaces, possibly glassy coatings, formed through repeated cosmic ray impact, melting microscopic patches and refreezing them instantaneously in the cold void. Such surfaces scatter light in a way that mimics artificial materials, but naturally sculpted by time radiation and interstellar erosion. All of this combined, the polarized dips, the early inversion, the grain alignment, the Faraday rotation, the reflectivity shifts constructed a picture of a comet that even stripped of speculation challenged the limits of comet science. A body shaped not by the sun but by the interstellar medium, a nucleus wrapped in processed dust, a veil shaped by plasma dynamics that danced with light. Polarization could not reveal the nucleus, but it revealed the veil. And the veil, once invisible, had become the central phenomenon, an interpreter between the comet and every eye that sought to see it. 3i Atlas was no longer simply an interstellar visitor. It had become a teacher, a reminder that the light we receive is not merely reflected. It is shaped, twisted, filtered, and transformed. And sometimes the medium becomes the message. Long before its coma unfurled into the inner solar system, long before any telescopic eye turned toward it, 3i Atlas had lived another life, one shaped not by our sun but by a star we will never know. Its chemistry, strange and lopsided even by interstellar standards, whispered stories about that distant birthplace. The dust grains scattered throughout its veiled shroud were not random fragments, but relics, memory-bearing minerals forged in an environment humanity has never directly witnessed. And among those relics lay the most telling clue of all: its chemistry was wrong for a solar system object, yet too coherent to be accidental. What emerged from spectral analysis, both from Earth and from space-based observatories, was a picture of a comet profoundly shaped by thousands of millennia of exposure to interstellar radiation. Cosmic rays, far more intense in the void between stars than within the solar system's protective bubble, carve their signatures into fragile molecules, breaking them apart, recombining them into stranger, darker chains. Over time, nitrogen-bearing organics deepen into complex tholins. Carbon monoxide, abundant in the outer disks of young stars, undergoes radiation-driven oxidation, transforming into carbon dioxide. While CO2 is not rare in comets, its dominance in 3i Atlas was startling. It suggested that the comet spent millions of years in conditions where CO was constantly irradiated, slowly converted into CO2, and trapped beneath a crust hardened by its journey. This process left behind a volatile inventory, unlike anything that naturally survives long in our solar system. Comets here age quickly. Sublimation erodes them, sunlight fractures them, collisions reshape them. But an interstellar comet can drift in cold isolation, preserving ancient compositions from a star's own protoplanetary disk. The chemistry of 3i Atlas thus became a kind of forensic map, a composition that held the ghost of its origin. One ratio stood out: an extraordinarily high abundance of carbon dioxide relative to water. Water should dominate a comet's inventory unless water had been depleted or locked beneath layers so thick that even perihelion heating could not easily reach it. CO2, being more volatile, escapes even through hardened crusts if pressure builds beneath. This would explain the comet's early and vigorous CO2-driven outgassing, long before its water signature rose to detectable levels. It also illuminated a deeper truth: the comet's surface was ancient, so ancient that its outer layers had been transformed almost entirely by cosmic ray chemistry. Such chemistry produces organic crusts rich in carbon chains, nitrogen-bearing molecules, and complex polymers. These molecules change the optical properties of dust, making it darker, more cohesive, and more likely to form large aggregates. Dust like this behaves differently from the fluffy, porous material typical of solar comets. It clumps rather than drifts. It aligns more readily under magnetic fields. It becomes electrically active under ultraviolet light. It can even form micron-thick glassy coatings where radiation has melted tiny regions and refrozen them instantly in interstellar cold. This was the dust shaping the visibility paradox. The thermal behavior of 3i Atlas added another layer to the mystery. Its temperature distribution was strange. Some regions appeared warmer than models predicted, others cooler. This kind of mismatch suggested an insulating surface crust with deep pockets of more volatile ice beneath. When CO2 escaped through microscopic fissures, it carried with it dust that had resided beneath the outermost radiation-processed layers, dust that still reflected an earlier, more pristine chemistry. In other words, the comet was shedding history in layers. The strange homogeneity of the large grains, so puzzling to researchers, could be explained by a combination of ancient radiation processing and slow thermal cycling in the interstellar medium. A comet drifting for millions of years through 310, Kelvin environments experiences gradual sintering edges soften, grains partially fuse, pores, collapse. Over time, dust becomes smoother, more reflective and more resistant to fracturing. It begins behaving more like engineered material than natural debris, but engineered by the cosmos itself. Then came the isotopic anomalies. Early measurements suggested carbon and oxygen isotopic ratios consistent with but not identical to solar values. Small deviations hinted at formation around a star of similar metallicity, but perhaps younger, or in a region of its protoplanetary disk that experienced different temperature and radiation conditions. Some researchers argued the comet may have formed around a red dwarf, where stellar flares and ultraviolet pulses would have supercharged radiation chemistry, early in its history accelerating CO2 formation. Others suggested a more massive hotter star where protoplanetary disk gradients produce extreme segregation of volatile ices. The chemical fingerprint pointed to an object born not in a chaotic disk like our Sun's, but in a disk where carbon was king, a place where sea-bearing molecules condense preferentially, or where the early stellar environment baked organics into layers deeper than any seen in the solar system. Such chemistry also explained the radar and radio anomalies recorded as the comet approached the solar wind. Hydroxyl emissions behaved oddly because they were being pumped not from pure water sublimation, but from a mixture where CO2-driven outgassing and charged dust complicated the excitation mechanisms. The result fluctuating line strengths, polarization shifts and ratios that refused to stabilize. A final clue emerged from the mid-infrared spectral slope, the presence of refractory organics, more typical of outer protoplanetary disks than mature comet populations. These organics subjected to cosmic rays and extreme cold-form structures that can survive aeons of interstellar drift. Their presence indicated that 3I Atlas had likely been ejected early in its home system's history, before gravitational shepherding could place it into safer orbits, as though nudged violently outward by a passing star or by the chaotic migration of giant planets. And so the comet carried with it not only chemistry from another star, but history stories frozen into layers of dust and ice, written in isotopes preserved by the cold exile between suns. It was this chemistry, exotic yet natural, that shaped the veil, that powered the CO2 jets, that anchored the large dust grains, that charged the plasma environment, that confused every instrument humanity pointed at it. The comet did not need to be engineered. Its strangeness was the product of time distance and the forgotten violence of another star's early days. Yet even as chemistry grounded the mystery, it deepened it, because nothing in the solar system had ever presented such a coherent, organized set of anomalies. Nothing had ever displayed such selective visibility, and nothing had ever carried a veil so stable, so structured, so resistant to both casual and professional scrutiny. The chemistry explained the comet's past. It did not yet explain its present. The next question, perhaps the most unsettling one, was whether the veil was purely natural at all. When the first models of the plasma veil appeared on preprint servers, the scientific world reacted predictably. Cautious curiosity on the surface, uneasy fascination just beneath. No one dared voice the thought directly. Not in early drafts, not in conference hallways, not in interviews where every word might become a headline. But the question simmered anyway. An unspoken presence lingering behind every anomaly. Was 3I Atlas simply a strange natural comet, or something more deliberate in its behavior? This was not the language of conspiracy. The researchers who entertained the question did so reluctantly, bound to rigor by decades of training. Yet the comet's consistent defiance of natural expectations forced a reckoning with possibilities that occupied the outermost fringe of scientific plausibility. The more natural explanation strained, the more the comparison arose quietly, almost apologetically, to engineered behavior. Not because anyone believed the comet was a machine, but because its environment acted with a kind of symmetry, coherence, and selective opacity that bordered on purposeful. But the inquiry had to begin where all scientific inquiry begins, with the natural. The leading natural interpretation held that 3I Atlas was an interstellar relic shaped by the extreme conditions of its birth system. If that system experienced intense flaring, rapid planet migration, or strong magnetic fields, the comet's chemistry and plasma environment could carry the scars. Its veil could arise from hyperactive CO2, sublimation driving ionization at unusual distances, a dense magnetized dust shell inherited from cosmic ray processing over millions of years, volatile layering, producing selective jets that interacted unpredictably with solar wind, charged aggregates aligning under magnetic stress, thermal fractures releasing dust in episodic magnetically ordered bursts. In this picture, everything was natural but rare, a perfect storm of physical conditions that happened to mimic complexity. And yet even within this framework, certain features remained stubbornly articulate. The selective visibility. The paradox at the heart of the phenomenon implied that the veil was not random. It behaved consistently across observation modes. High-resolution sensors saw blur, low-resolution sensors saw structure. Short exposures lost detail, long exposures recovered it. Ultraviolet wavelengths recorded chaotic ionization. Red and infrared slipped through relative calm. This was not noise. It was a systematic modulation of visibility based on wavelength and exposure time. A natural veil could do this, but the precision of its selectivity troubled many. The second source of discomfort came from the veil's spatial symmetry. Plasma usually forms chaotic envelopes around comets, plumes, streaks turbulence, ragged gradients. But 3i Atlas displayed coherence arcs boundaries quasi-spherical layers. Not perfect spheres, but enough regularity to suggest a magnetic topology orbiting the nucleus. In the natural interpretation, this required an unusually persistent dipole-like magnetic field embedded within the comet's dust or crust, something possible but extremely uncommon. Some scientists pointed out that even modest remnant magnetization could under interstellar conditions carve stable plasma forms, magnetospheres in miniature. If 3i Atlas had developed such a field early in its history, cosmic ray processing might have hardened and preserved it over eons. The comet would then carry a fossil magnetic signature through interstellar space, shaping plasma and dust into semi-ordered layers. The veil in this model was not engineered, it was archaeological. Others, however, saw something beyond archaeology. In private discussions, a few researchers explored the possibility, carefully bracketed as an intellectual exercise, that the veil might behave more like an adaptive medium than a passive one. Some features were difficult to reconcile with pure stochastic physics. The veil's thickness appeared to correlate with observational geometry. Magnetic fluctuations detected from Mars orbit suggested internal organization rather than chaotic flow. The dust grains displayed a surprising degree of alignment, hinting at long-range order. Jets seemed to phase in and out of visibility with a rhythm faintly suggestive of feedback. The veil's opacity sometimes increased exactly where high-resolution sensors probed deepest. These were not proofs, only patterns, and patterns can mislead. Still the question arose, could a comet develop through entirely natural processes a plasma environment so coherent that it resembles a defensive or cloaking structure? The answer from physics was a tentative yes. Plasma can self-organize. Magnetic fields can trap charged dust. Ionized envelopes can mimic the behaviors of engineered shields. No intent is needed, only the right combination of chemistry ionization, charge distribution, and environmental stress. But the deeper philosophical question refused to soften. Why did 3i Atlas behave so precisely at the intersection of visibility and concealment? Could natural selection at the level of cosmic debris produce objects whose behavior appears engineered simply because only the stable survivors reach interstellar space? Or was this coherence simply the anthropic illusion of a dataset too thin for clarity? Scientists recoiled from speculation, yet some allowed themselves quietly to outline the theoretical possibilities if the veil were not natural. A plasma sheath used as radiation shielding, an adaptive layer controlling thermal regulation, a magnetic envelope designed to preserve volatiles, a mechanism to reduce sublimation loss during interstellar travel, a stabilization structure for long-term drift. Again unlikely, almost certainly unnecessary, but not physically impossible. The prevailing scientific stance remained resolute. The veil is natural, a rare but plausible product of interstellar evolution. But the fact that the engineered interpretation could not be dismissed outright gave the mystery a new dimension. Not a declaration of alien origin, never that, but a reminder that nature can produce effects so complex, so self-organized, that the boundary between natural order and perceived design blurs. 3i Atlas did not need to be artificial to appear intentional. It only needed to be ancient, altered, hardened, magnetized, and veiled by the long memory of another star. In the end, the question of natural versus engineered intent did not fracture the scientific community. It humbled it. It reminded physicists and astronomers that the universe does not owe us simplicity. That chaos can sculpt structure. That time can chisel coherence. That plasma dust and radiation can perform a choreography that looks deliberate only because complexity often feels like will. The veil remained mysterious but no longer inexplicable. It remained unsettling but no longer unimaginable. A comet could be strange without being constructed. It could be coherent without being alive. It could be veiled without meaning to hide. And yet as the data continued to accumulate, one truth became inescapable, intentional or not. The veil acted with a precision that demanded deeper scrutiny. The next step in that scrutiny would come not from amateurs or spacecraft imagery, but from the faintest signals the comet had ever given off its whisper in radio wavelengths. Long before the visibility paradox captured the public imagination, long before the plasma veil became the leading hypothesis, the most delicate clues about 3i Atlas had already been carried to Earth on wavelengths far quieter than light. Radio waves, soft, ancient, patient, have a way of slipping through chaos. Where dust blinds, where plasma scatters, where short wavelength photons lose coherence, radio frequencies often remain calm, gliding past turbulence with a serenity that borders on indifference. It is in this domain, the domain of the long and low, that 3i Atlas revealed a different face, one unblurred, unhidden, and strangely articulate. The first radio detections targeted the hydroxyl radical OH, the familiar daughter product of water photodissociation. When sunlight splits water molecules in a comet's coma, OH becomes visible at specific radio frequencies, its spectral lines predictable, stable, almost architectural in their precision. But 3i Atlas complicated even this simple chemistry. Telescopes tuned to the 18-centimeter OH lines detected emission, yes, but with a ratio that defied standard pumping conditions. One of the lines was unexpectedly suppressed. Another appeared stronger than models could reproduce. The anomaly was subtle but persistent, as though the environment around the comet altered the excitation of OH molecules in a way Earthbound models had never accounted for. Normally such deviations hint at density effects, collisions, or electron interactions. In 3i Atlas, the deviations were rhythmic. Over nights, the line intensities wavered, not randomly, but with a faint periodicity, as though the surrounding plasma sheath modulated the radiation fields affecting OH molecules. The idea was unsettling, not because it hinted at intent, but because it suggested structure of veil, not only scattering visible light, but shaping radio excitation itself. Then came the carbon-bearing species. CO was expected. CO2 was expected. But the comet refused to give up its full inventory in the infrared. Radio telescopes less susceptible to the veil distortion stepped in. Millimeter-wave instruments searching for carbon monoxide found signatures weaker than expected odd given the CO2 dominance. Some speculated that CO exposed for millions of years to interstellar radiation had been converted to CO2 deep within the nucleus. Others suggested that CO existed but could not easily escape beneath the hardened crust, emerging only through narrow vents that radio instruments did not easily resolve. In any case, the mismatch reinforced the comet's chemical peculiarity. The next surprise arrived from polarization in radio wavelengths. Radio waves can pass through plasma with little scattering, but they can experience Faraday rotation, an effect in which the polarization angle rotates as the wave moves through a magnetized ionized medium. Observations of 3i Atlas revealed rotation more extreme than expected for a typical comet. The amount of rotation implied either a higher electron density or a stronger magnetic field along the line of sight. Neither option was comfortable. Electron densities high enough to induce such rotation would require a plasma sheath far denser and more coherent than any standard coma. A strong magnetic field would be equally exotic. Comets do not generate intrinsic fields of such magnitude. Yet the rotation was undeniable. Something magnetized, something ordered lay between the nucleus and the observer. Radio astronomers began to suspect that the veil was not merely a scattering medium, but a magnetically structured shell, not a true magnetosphere, but a quasi-magnetized environment, shaped by ionized CO2 dust charges and solar wind interactions. Such a shell could exist naturally, but only under extreme conditions rarely witnessed in the solar system. The veil was beginning to look less like a loose cloud and more like a boundary. The strongest evidence arrived weeks later when an array of radio telescopes measured the comet's continuum emission in longer wavelengths. Dust emits thermally across the radio spectrum, but 3i Atlas displayed an emission slope that rose too smoothly, too uniformly, suggesting a dust population dominated by large compact particles. This aligned perfectly with polarimetric results. The dust was ancient, hardened, and uniform. More importantly, radio emission did not suffer the same structural distortion seen in visible light. Where Highrise saw blur radio maps saw gradients faint, yes, but present. A slight thickening along one edge of the coma, a subtle asymmetry consistent over multiple nights. A persistent brightness tail not aligned with the visible tail but shifted as if tracing a different physical structure. Some theorists suggested that the radio tail traced zones of enhanced electron density regions where the veil collected charged particles into coherent flows. If true, the radio images were not showing dust at all, but the skeleton of the plasma environment itself, its contours revealed by thermally emitting grains spiraling within magnetic boundaries. This interpretation was bold. Yet it explained much the conflicting jets seen by amateurs, the symmetric blur seen by spacecraft, the polarization, anomalies, the thermal inconsistencies. The veil was not only changing visibility, it was shaping the entire physical layout of the coma. Radio data also offered something no optical dataset could: stability. Where visible images flickered with turbulence and sharpness, differences radio signals remained steady. Overnights, the comet emitted with near-mechanical regularity, suggesting that whatever turbulence existed in the veil lay at scales too small to disturb long wavelengths. The stability implied an underlying order, a slow, large-scale structure guiding the smaller chaotic motions. In one particularly intriguing set of observations, a trio of radio telescopes captured faint quasi-periodic fluctuations in continuum emission. These fluctuations were too slow to represent rotation of the nucleus, too regular to represent noise, and too subtle to force any confident conclusion. But their timing faintly matched periodicities inferred from amateur imaging of brightness, modulations features that may have reflected rotational harmonics of the nucleus, or the dynamics of the veil itself. For the first time, two different domains, optical and radio, hinted at the same unseen rhythm. The veil was not static, it pulsed, yet radio waves pierced its depths with an ease denied to visible light. In radio maps, the comet's coma extended farther than in the optical revealing tails invisible in photographs. Some of these tails traced solar wind flow, others curved oddly as if shaped not by solar radiation pressure alone but by interactions with a structured charged envelope. Still nothing in the radio data revealed the nucleus directly. The veil was transparent at long wavelengths, but still dense enough to obscure the small rocky or icy core. The heart of 3i Atlas remained unseen, silent, shielded, but the whisper in radio wavelengths had done its work. It had proven that the comet's invisibility was not a flaw in optics, not a trick of geometry, not an illusion of amateur processing. It was physics and environment that selectively modulated the universe's messages depending on how they were asked. In light 3i Atlas blurred, in radio it spoke, and what it said in long calm wavelengths was this: the veil was real, structured, and alive with motion. The next challenge would be integrating these revelations with the global effort to observe the comet. From every vantage point, humanity possessed an effort that would turn the visibility paradox into a full spectrum puzzle spanning planets. As the comet drifted deeper into the inner solar system, its paradox grew too large for any single observatory mission or nation to constrain. What had begun as an odd mismatch between amateur images and spacecraft data now demanded a coordinated multi-agency campaign, a tapestry of observations stretching from Earth's deserts to snowy mountaintops, from orbiters around Mars to robotic scouts at Lagrange points. Only by viewing 3i Atlas from many angles at once could humanity hope to understand why it hid from some instruments, yet revealed fractured glimpses of structure to others. The resulting network of eyes was unprecedented for an interstellar visitor. Each vantage point contributed its own fragment of the truth, and each fragment sharpened the paradox. From Earth, the European Southern Observatory trained its enormous optical telescopes on the object. The very large telescope armed with adaptive optics attempted to pierce the veil with its precisely corrected starlight. Instead of clarity, it saw a diffuse glow remarkably similar to what Highrise had recorded from Mars orbit. The high-resolution advantage instruments capable of resolving features just tens of kilometers across collapsed into the same luminous haze. Adaptive optics engineered to cancel Earth's atmospheric turbulence offered no help. The veil, if present, remained impervious. The Subaru telescope in Hawaii, using a combination of visible and near-infrared instruments, captured something slightly different, a fainter symmetry along one edge of the coma that repeated across multiple nights. It wasn't a jet exactly. It wasn't a tail either. More like a persistent zone of brightness offset from the nucleus. The feature aligned intriguingly with the radio asymmetry detected earlier, hinting that multiple wavelengths were tracing the same hidden structure. Subaru had not pierced the veil, but it had glimpsed its outline. In Chile, the Atacama Large Millimeter, Submillimeter Array ALMA continued its radio surveillance. Its immense dish array, spanning up to 16 kilometers, mapped the thermal emission of dust grains that escaped the visible domain entirely. Yet even ALMA, designed to cut through dust clouds and star-forming regions, recorded peculiarities. The dust distribution was too narrow, the gradient too smooth, the tail's curvature too stable. These were the signatures of a dust population shepherded by forces not typical in comets, forces that made sense only in the presence of a structured magnetized environment. Meanwhile, from space, the James Webb Space Telescope observed from its vantage at L2. JWST, using its mid-infrared instruments, attempted the most daring feat to image the nucleus through wavelengths, where the veil's interference might be minimal. What it saw was not a resolved nucleus, but a warm core whose thermal profile contradicted every model. Some parts of the core radiated as if the dust were thicker than expected. Others radiated as if the veil were thin. JWST could not see through, but it could feel through recording thermal gradients that described the veil's density, like a blind hand tracing the contours of an unseen sculpture. Even stranger were the inconsistent thermal signatures that varied on timescales, too short to reflect true temperature change, changes likely caused by flickering plasma densities not the comet's surface. JWST was staring not at a nucleus, but at heat modulated by the veil's own shifting internal architecture. From closer to the comet's path, ESA's solar orbiter detected disturbances in the solar wind consistent with a compact magnetically structured obstacle. Not a magnetosphere, but something magnetosphere-like. Enough to divert charged particles subtly enough to create a measurable ripple in the heliospheric flow. A natural object could do this under the right conditions, but few comets ever had. NASA's Parker Solar Probe, too deep inside its solar grazing orbit to see the comet directly, still recorded perturbations in the solar wind downstream of the object's projected path. Though the connection could not be definitively proven, the timing aligned with intervals during which Earth-based telescopes saw features sharpen and fade. China's Tianwen-1 orbiter, equipped with sensitive optical imagers, contributed an unexpected perspective from its position around Mars. Unlike Highrise, which had struggled with blur, Tianwen-1 captured a faint, somewhat structured coma, more consistent with amateur images. The difference appeared to stem from exposure time and wavelength selection, another confirmation of selective visibility. India's Astrosat spacecraft, observing in ultraviolet, detected intense ionization spikes in the coma, yet no clear jets. The veil dominated the UV domain, hiding deeper structure while glowing fiercely. Even amateur astronomers became an integrated element of the global campaign. Their long-exposure narrow-band images provided continuity when larger observatories were clouded out or pointing elsewhere. Their data, once supplemental, became essential. They could trace changes in coma geometry over hours or days, revealing rhythms that large instruments forced to schedule observations in blocks could easily miss. When all these vantage points were combined, radio gradients from ALMA thermal pulses, from JWST asymmetries, from Subaru blur, from Highrise, and VLT UV flares from Astrosat solar wind ripples, from Parker and solar orbiter, a picture emerged that was far stranger than a comet, yet still firmly within the boundaries of physics. The veil was not a layer, it was a system, a dynamic structured multi-wavelength environment sensitive to solar wind velocity, magnetic flux, wavelength of observation, exposure time, rotational phase of the nucleus, and perhaps even to the comet's own internal charge distribution. No single observatory could map it. No single wavelength could reveal it. Only the full network Earth-Mars space amateurs could assemble its mosaic, and that mosaic was beginning to show the first hint of order a faint repeating pattern in the veil's brightness peaks and density troughs, a rhythm faintly detectable across visible infrared and radio observations, a cadence that did not match the comet's orbital motion nor its likely rotational period nor solar wind compression cycles. A drumbeat with no clear drummer, or perhaps simply a natural pulse of plasma under complex magnetic stress shaped by chemistry humanity, had never before encountered alien but not unnatural. It was enough to set the stage for the final step in humanity's effort to understand the visitor applying new tools, high-speed imaging pipelines, artificial intelligence and next-generation observatories to probe a veil that seemed almost designed to resist. By the time every major observatory had turned its gaze toward the interstellar visitor, the paradox had expanded beyond the reach of conventional interpretation. The comet had become not merely an object of study, but a test and examination of the assumptions baked into every imaging pipeline, every calibration routine, every model of dust and plasma behavior that astronomers had relied upon for decades. To see 3i Atlas, clearly humans no longer needed more powerful telescopes. They needed different ways of seeing. The first attempts to reprocess spacecraft data revealed the fragility of long-standing assumptions. High-rise images, once dismissed as featureless, were fed into pipelines modified to treat the blur not as noise but as signal, an opportunity to decode the veil rather than penetrate it. Machine learning models trained on simulated plasma-shrouded comets began to identify subtle gradients in the brightness profile. These gradients were not nucleus features. They were density modulations, ripples in the veil. Under this new analysis, the images became meaningful. Not sharp, not resolved, but interpretable within a framework that assumed the veil itself was the subject. The same transformation unfolded across other datasets. JWST thermal maps once interpreted through traditional comet models were re-evaluated using radiative transfer simulations that incorporated electrostatic dust alignment and plasma scattering. Suddenly, the hot and cold patches made sense not as contradictory thermal behavior, but as the veil's internal structure passing in front of the nucleus, modulating the infrared signatures like clouds drifting across a lamp. ALMA's millimeter wavelength maps too were reanalyzed using algorithms that accounted for charged dust spiraling within magnetized flows. What had looked like a smooth gradient now revealed faint thread-like features, subtle ridges of enhanced emission, tracing pathways through the veil. These were the first true visualizations of the veil's architecture, captured not by any camera, but by models refined to interpret the world through the physics of its distortion. Artificial intelligence became indispensable, models trained on solar wind plasma interactions, cometary ion tail instabilities, magnetic reconnection behavior, and turbulence and charged dust environments were fed observational data from Earth and Mars. AI found correlations no human eye could detect, tiny synchronized fluctuations in brightness across different wavelengths, faint periodicities linking amateur images with radio emission, peaks, micro-oscillations in the veil density that aligned with solar wind spirals measured by ESA's solar orbiter. It was the first sign that the veil was not random, not static, not chaotic. It was responsive not by intent but by the natural feedback loops inherent in plasma environments interacting with rotating bodies. As the nucleus spun, its outgassing fluctuated. As outgassing fluctuated, ionization changed. As ionization changed, dust alignment shifted. As dust alignment shifted, scattering behavior adjusted. A full self-contained feedback cycle, creating the illusion of behavior when only physics acted. New tools turned confusion into coherence. The more the data was stitched together, the clearer the story became. The veil was a system governed by a small set of underlying parameters: rotation, chemistry, charge, solar wind conditions, yet capable of expressing complexity so intricate it nearly resembled intention. But perhaps the most remarkable shift came not from reprocessing old data, but from the next generation of observatories brought online specifically to study 3i Atlas. Experimental high-speed imaging arrays designed to capture bursts of data at hundreds of frames per second recorded the veil's microturbulence. These instruments saw flickers, millisecond-scale distortions invisible to conventional exposure times. When analyzed, the flickers traced organized flows swirling like slow-motion auroral currents wrapped around the comet. Spectrographs optimized for extreme faintness recorded rare emission lines from ionized carbon and oxygen. These lines were signatures of recombination at the edges of plasma sheets not visible in bright comets, but evident here because the veil was the main actor, not the nucleus. Polarimeters with high temporal resolution revealed oscillations in the polarization angle that matched the veil's microturbulent pulses. These rhythms, once mysterious, now aligned with models predicting torsional waves in magnetized plasma structures. The comet was no longer merely observed. It was being mapped layer by layer, function by function, across 100 tools that finally spoke to one another through shared models rather than isolated interpretations. Yet even as clarity grew, something more profound became evident. The veil was not an anomaly of this comet alone. It was the likely normal state of many interstellar objects preserved, radiation crusts, ancient volatile layers, hardened dust, and magnetized sheaths shaped by the long loneliness between stars. 3i Atlas had simply been the first to pass through the inner solar system at a moment when humanity possessed the tools to recognize the veil instead of mistaking it for blur. Still, understanding did not diminish mystery. In fact, the final synthesis of all data offered a quieter, deeper strangeness. The veil was too delicate to survive close passage to the sun, yet it had endured. It was too structured to arise from random turbulence, yet it was natural. It was too precise in its selective visibility to be dismissed as coincidence, yet it obeyed every known law of physics. A system perched at the boundary between chaos and order, born of star and void speaking through distortion. As 3i Atlas continued its arc around the sun and began drifting back toward the darkness between systems, the veil slowly thinned. Features that once flickered ceased. Jets that never fully revealed themselves quieted. The structure dissolved into the ordinary coma of a quietly receding comet. Its secrets were not exhausted, but they were receding, vanishing behind the horizon of observation, and so the global campaign turned reflective. The instruments powered down, the images stopped updating, the simulations wound toward completion. The visitor was leaving. The veil, once dense and bewildering, now stretched into a tenuous ribbon of dust and ions trailing behind an object once too strange to see clearly. It was time to let the sky fade and the questions remain. The comet drifts now where sunlight softens, where the solar wind grows thin and slow, where the quiet resumes its ancient dominion. Its veil, once bright with turbulence, alive with invisible motion, fades into a gentler haze, no longer stirred by storms, no longer forced into revelation by the gaze of curious worlds. The structure that once confounded every instrument becomes diffuse, then delicate, then finally indistinguishable from the darkness that cradles it. Whatever it carried from another star now settles into a silence deeper than distance. The observers, whose nights were filled with flickering screens and restless wonder, release the last data streams and let the noise fall away. Their tools rest. Their models, once crackling with contradictions, quiet into something softer, unfinished yes, but no longer discordant. A mystery does not shrink when explained. It simply changes shape, becoming gentler at the edges, easier to hold without tightening the grip, and in that softened shape lies something comforting. The universe revealing not certainty but continuity. A comet from another sun shaped by long and solitary travel can still surprise the worlds it visits. It can carry its history without needing to share it fully. It can be strange without being menacing, complex without intention, hidden without hostility. It can simply be itself, an old traveller brushing past a young civilization. As 3i Atlas fades into the distance, the light it scatters becomes dimmer, warmer, almost tender. A reminder that not every visitor arrives to confront. Some arrive simply to pass by, trailing questions like dust. And so the sky returns to its quiet rhythm and the comet continues its path into the deep calm between stars. Sweet dreams.